Good morning, everybody, and welcome to the felicitation function of the Olympiad medalists of 2019. This function is organized by the Homi Bhabha Center for Science Education in collaboration with the TIFR Endowment Fund and is supported by the Infosys Foundation. So welcome to all of you, the Olympiad medalists, the leaders, observers, our colleagues from HBCSE, and also the students from AES Junior College. It's very nice to have you here. Welcome. So as per the tradition of this function, we have two parts in this. In the first half, in the morning, we have two lectures by eminent scientists. And today, we are very glad to have with us Professor G. Ravindra Kumar from TIFR and Professor Gagandip Kang from THSTI Faridabad. So we will start with Professor Ravindra Kumar's lecture, and then in the later half, we will have the formal function after a break. Professor G. Ravindra Kumar is an alumnus of BITS Pilani and IIT Kanpur. He obtained his PhD in 1990 from IIT Kanpur. He has been at TIFR since 1992 and is presently a senior professor in the Department of Nuclear and Atomic Physics. His areas of interest are experimental studies of high-intensity laser pulse interaction with matter, creation and understanding of extreme states of matter, and nonlinear optics. And he was elected a fellow of the Indian Academy of Sciences in 2004 and of the Indian National Academy in 2008. He has received many awards. I will just list a few here. He received the B.M. Birla Prize for Physical Sciences in the year 2000, the S.S. Bhatnagar Prize for Physical Sciences in 2003, a DA Outstanding Investigator Award in 2005, J.C. Bose Fellowship in 2010, and the Infosys Prize in Physical Sciences in 2015. He has been on the International Committee of Ultra-High Intensity Lasers since 2008 and is currently the co-chair of this committee. He is a life member of the American Physical Society, the Plasma Science Society of India, and the Indian Laser Association. He is a member of the Optical Society of America. So a very distinguished speaker. We are very glad to have you, Professor Ravindra Kumar. Please, you can begin your talk.
Good morning. Can you hear me? Looks like I need to. Yeah, can you hear me now? With this collar mic.
It's okay.
It's okay? Yeah. Good. So it's very nice to be here. Bright young people, several colleagues I know, and friends from all over. And nice to be among the, to start the day with looking at bright young faces who are going to conquer and achieve great things in the future. So I thank Ravi and Anvesh for getting me here and suggesting that I give this talk. And of course, I thank the Infosys Infosys Foundation for initiatives like this and several others that they do to encourage science in this country. So this is the talk that I have tested out a little before. So perhaps you can help me shape this a little better. And let's see how it goes. So I'm going to talk to you about extreme light, right? So in the morning, it's not a good thing to begin with extremes. Most people barely wake up, at this time. So you're talking about extreme light and extreme state. So people are wondering, what is all this fuss about? So maybe we'll make some sense by the end of this talk. So this is what we call ourselves uphill. And maybe you can look at this picture. I am here, and there is something here. And this is quite symbolic of what I'm going to talk about. So perhaps keep this picture in your mind as the talk progresses. Okay, so TIFR has many locations. This is, of course, a location which all of you are familiar with, but we have another one at the end of the city in Colaba. And that's where our lab is located, right next to the sea. And so please do visit in case you haven't been. And this is the plan that I'm somewhat ambitious for a 45-minute talk. But nevertheless, I'll try and cover as much as I can, trying to give the basics. And whatever examples I give are more by way of illustration of the kind of things that are possible. So let's see how much we can actually cover. And I'm also trying to advertise my own review article, a tutorial review that I wrote 10 years ago. Because it's a tutorial, it's still relevant, I believe. So please, you can get lots of basic ideas about this field from this article which was published a decade ago. Okay, so let's begin with some questions. You know, all of us are asking and answering questions all the time. So let me begin with my own set of questions. And the first thing is, what powers the universe? All of us know that the visible universe is full of stars, right? Stars, planets, objects of various types, exploding, living, you know, some of them lead very, very violent lives. And then lots of things happen in the universe, and we capture this information through various means of observation. So basically, my take on this is that, you know, anything that is so self-absorbed like a star actually destroys itself, right? So it collapses under its own gravity, compression, heating happen. At the end of it, high density, hot matter is what actually forms, which is what we call plasma, we call it a degenerate state, we call it various things depending on who you talk to. And obviously the reason for all this, the power is coming from nuclear fusion. And some stars are in equilibrium when these balancing, competing pressures actually match. And some others, when one of them overwhelms the other, they have their own fate. Some of them explode very violently, and some of them collapse to you know, nearly singular kind of states like black holes and so on. So the point is that lots of things are happening in a star, even though to us it looks like it is just constantly emitting light, but there's lots of dynamics going on inside. And everything about the star, and in fact most of this visible universe, is all staggering by way of numbers. So the temperatures are of the order of 100 million Kelvin. Given that the room temperature is 300 Kelvin, you know how large this is. The pressures, we are at 1 bar pressure, but the pressure inside a star in many environments can be something like gigabars, a billion bars, a billion atmospheres. The densities are much, much larger than what we encounter on the Earth, 1,000 times larger typically than the density of water, which is 1 gram per cc at 4 degrees C, as you all know. And the magnetic fields, this is something that amazes most people, that stars can have magnetic fields which are billions of Gauss, trillions of Gauss, in fact 10 to the 15 Gauss, and compared to the paltry magnetic field of the Earth, which is only you know, barely a Gauss. So having said all this and looking at the heavens and admiring lots of things that are going on, the immediate environment in which we live, which is what it makes it very difficult for us to believe that there are such spectacular things happening, is very low energy. The densities are normal at which all of us exist and we do things. There's equilibrium, there's weather patterns which keep changing periodically, and all these are of course very, very crucial for sustaining life. Otherwise we won't be here wondering about what the stars are made of. But it is not right to think that the Earth itself has only some kind of a placid environment, some normal things happening. Because if you look at something like an earthquake or lightning, you immediately know that these are phenomena which are extremely energetic, right? They release huge amounts of energy, and they are our match. So what we see, experience on the Earth, which in some sense matches what happens in the rest of the universe. So this is a great picture of lightning striking a busy city. Hopefully no damage done there. And so this is a very nice picture. It tells you what kind of currents are passing through the atmosphere, what kind of energy is released. And lightning is something that we are still trying to understand, trying to come to grips with. And some of us, by the way, are also trying to control lightning, like so that it doesn't hit populated areas, and probably it can be channeled away elsewhere. But if you have interest in it, we can talk about it at the end of this talk. And so this is another thing that, you know, we think that on the surface of the Earth everything is moderate, nice, simple, but cool surfaces contain extremely hot interiors. Like many people, they are very calm outside, but you know, if you probably probe them a little, they reveal their sort of extremely a different state of mind that they are actually that they convey. So cool surfaces contain hot interiors. What I mean is that if you have 1 bar pressure here, but try and go inside the Earth or inside a planet, and you see that the pressure goes on increasing, And there comes a pressure region, something like 8 megabar, 10 megabar, where you have actually metallic hydrogen. Hydrogen for most of us is a gas, right? On the earth, it's a gas. But if you put subject hydrogen to a pressure which is something like 8 megabar, it becomes metallic. What does it mean for a gas to become a metal? It's a very interesting question, right? But these things can be explored deep inside planets. So you are sitting here observing lots of things, doing experiments here, but if you go deep inside, you encounter situations which are extremely abnormal and which are very, very interesting, because here matter has been pushed to a different level of excitation, right? And if you go further, it goes much further, and of course, the cores of many planets are, what the Earth is made of. What is the Earth sitting on? At the deepest core, as most of you know the plate tectonic theory of the Earth, right? That we have these plates which are deep inside and they are moving constantly, and hence, you can have, when the dynamics of these plates can cause earthquakes and so on and so forth. So this is true of any planet. So if you are not here, you either go far above and look at the sky, or deep inside and look inside. In either case, you have extreme conditions, right? Which is very interesting. So how do we understand the stars? I don't need to tell people here, particularly the bright young guys, that we have lots of probes. We sit on the Earth, right? Or we march into space, launch satellites, put telescopes there, and we get various information. And these things are rather cheeky, and I hope they don't offend anyone, that I tell my astro colleagues that you're always living in the past, right? They never get to the present. Meaning, this thing exploded 1 billion years ago, and now I have a signal that has reached my telescope, right? So I'm looking at things which happened, and most of us are told, like, just move on in life, don't look at the past. But astrophysics by nature, by observation, has to look at the past. And the thing is that these signals come and go. So if you want to watch what happened long ago, you either take the signal when it comes as it comes, or it's gone forever, right? You can never get the same signal again unless a similar event happens elsewhere, and which again sends you a signal, and which you are fortunately able to actually get it in your telescopes. So I'm very proud and happy to present that TIFR does this in very great style, and this is one of the best radio telescopes that we have in the world. And this is entirely a TIFR design, construction, which is there 150, 200 kilometers from here. So please do go there and look at this telescope and marvel at what we have done to observe the radio signals from the universe. So this is a radio telescope, giant meter wave radio telescope, and so there are several dishes in a certain configuration, and you stand under this dish and look up, and you truly feel the marvel of this instrument, the fact that we have built this and we can get radio signals from far, far in the universe. And this is what we are doing on the Earth, but we have also leapt into the space, and this AstroSat project, on which TIFR has placed 3 payloads, was launched in 2015. It's gathering lots of data, and bright young people are needed to look at the signals that have been collected, the signals that are coming, and make sense and do exciting astrophysics in the near future. But let me come back. I said that astrophysics is done in a particular way, and we are getting lots of information. And as always, astrophysics is the most exciting subject that you can think of, because there's so many things that we can discover, that we are discovering with better technologies and so on. But if you look at a small-time guy like me, a small lab guy, we do things like this. We observe, we systematize, we see patterns, and more importantly, we do an experiment where we create the conditions that we want to observe, right? So we want to make repeated observations. We poke some system with some impulse or some drive, and then look at signals that come. And we do this repeatedly. We do this maybe 1,000 times, we do it 10,000 times, and then keep on collecting data. And we have control on whatever parameters that we have, and so we change one parameter at a time, and then try and see how the result varies with that parameter. And these things are obviously not possible in astrophysics, right? Because you say that this thing is happening somewhere deep in space, and the signals just come. I mean, I don't have any control over the process there, and nor can I say that, can it happen again and again. I mean, that's asking for too much to say, the same process occurs repeatedly in an astro system. So the answer is usually a no, but if you talk to some people, there's a little answer here. It says perhaps you can create those conditions right in the lab. Right? I'll let a minute for this to sink in. What I'm making is a statement that while the stars are huge, they're doing spectacular things and signals come to you, a bit of what happens inside a star can probably be done right in the lab on the Earth. And wouldn't that be great? How do you do this? Well, people have tried all sorts of things because, as I said, most of the universe is in this extreme state of excitation. And while we can do experiments to understand physical systems in the lab on the Earth under normal conditions are low temperatures, rarefied ideal gas conditions and so on, it's really nice to know what happens in a complex high energy density system like that inside a star. So people have tried nuclear explosions, which are rather dangerous. I don't need to tell you that. And people have launched currents through wires, large amount of currents through lots of wires, which then explode and they compress matter which is in between, and they compress everything that is in the neighborhood and then create these kind of extreme conditions for a while. And the first is, I don't need to tell you, it can be a runaway reaction and there's a huge pollution fallout. We don't want to do that. It is still, the second one is more under our control, but it's still quite destructive because everything explodes, right, once the current is passed. And the problem is that while these things are done, scaled down or much, much smaller versions of the stars are possible to create and study on the Earth, either by these means or something else, which is much safer, much more exciting, much more interesting, and which is rather nice to do, right? So this is the alternative that I am proposing, that we use at TIFR and at several labs around the world, which is the high power pulse laser. So how do we do that? So all of you know that if you have a light source, like this, for example, I have a light source which is in my hand, which is pointing towards the screen. And if I have to increase the intensity, what do? All of you have done this experiment. You say, just give me a lens and I'll focus the light, right? So the focused light has, we all know that it has higher intensity at the focal spot than what it has in the unfocused beam. So that is what I call spatial squeezing, right? I'm trying to squeeze the light into a smaller and smaller area. So locally I create a high intensity. And you have done that with sunlight and a lens and probably focused it on a paper and burned the paper. Most kids do that. And I can see a smile there, right? Okay. So now imagine squeezing light into a short time. Rather counterintuitive for most people, saying that what do you mean by squeezing in time? I know what it means to squeeze in space by a lens, but what is squeezing in time? So what I mean is something like this. So if you squeeze light into a small duration like a nanosecond, like say you take 1 joule and squeeze it into a nanosecond, that means that you emit it as a burst of a nanosecond, a burst lasting all of a nanosecond, which is a billionth of a second, and then immediately it has what is called a peak power, which is given by this 1 joule by 1 nanosecond, which is 1 gigawatt. So if you had 1 joule in 1 second coming out, the light coming out steadily over 1 second, that actually is just a watt of power. But if you squeeze it in a burst, and the burst has a power which is a peak power which is 10 to the 9 watts, which is a billion watt, right? So what happens when you start creating bursts like this? How does such light interact with matter? So that's the next question to ask. So, well, if you squeeze it, as I said, even further into something like a picosecond, which is 10 to the minus 12 seconds, you actually produce something called a terawatt, right? So terawatt is trillion watts of peak power. Okay, so let me give you a feel for this, and before I tell you what happens to the physics of the system with which this light interacts. So probably this is very layman, but apologies if you already know this. So a femtosecond is a millionth of a billionth of a second, right? So, or a thousandth of a second. So if you look at it like this is 1 by so many zeros, or 1 decimal followed by this many zeros and a 1. So that's 1 femtosecond. And correspondingly, the power, because as you squeeze light into shorter and shorter times, the power goes up more and more. So you can just see that I told you about a gigawatt, which is 1000 million or a billion watt, excuse me, and then a terawatt is 1000 million watt, a petawatt is 1000 terawatt. So in terms of peak power, this is not average power, this doesn't come out continuously throughout the second, but this is just emitted in a burst. And so you can see that the scales of power that we normally deal with in our lives, like 500 megawatts or 1 gigawatt, are much smaller than what a peak power of a light pulse can produce. So this is how lasers have sort of leapt up in their intensities over the years. Laser was invented in 1960. By the 80s, people had already produced gigawatt pulses, and there was a major revolution which happened in the 80s, which sort of caused a jump by 3 orders of magnitude, and after that it has been climbing this inexorable, this curve has been is being climbed very, very rapidly. And these days there are petawatt scale lasers. People are talking about 10 petawatt. They are even talking about 100 petawatt. 100 petawatt will be 10 to the 17 watts of power. 1 petawatt is 10 to the 15, right? And if you look at the intensities, when you focus such light onto a small spot of something like 10 microns or so, you get intensities which are 10 to the 21 watts per centimeter square. 10 to the 21, you have no feel right now, but in a few minutes you'll appreciate what this actually means. 10 to the 21 watts per centimeter square is a monstrous kind of intensity, and let's see what it does. So this is supposedly a picture of the first laser invented by Theodore Maiman, and this is a big laser which is in one of the facilities around the world. I think this one is Japan, which produces this high peak powers. Now, to understand what all these numbers mean, let's look at some very, very basics. So light interaction with matter, most people can get by with just this picture of how light interacts with matter, right? All you say is that there is this electron attached to the nucleus, usually a valence electron, and light comes, and this is attached by what? It's attached by a Coulomb interaction, and that Coulomb interaction is, you can imagine it like a spring, right? So this is basically a spring mass system. The electron is a light mass, this is the heavy mass which is actually a support to this electron and holds it there, and now light comes. What does light come? Light comes and sort of shakes this electron a little, and once it shakes, the electron starts electron is displaced from its mean position. So it comes with some parameters, frequencies, wave vector and electric field, goes out modified by in these parameters, and the reason it happens is that it induces a dipole moment in this by oscillating this electron, which is given by this expression. So the dipole moment is directly proportional to the electric field, and the coupling constant is what is called a dipole or the electric susceptibility of the atom, right, for this valence electron. And the re-radiation is given by this wave equation, which is derived from Maxwell's equations. So this, as all of us know, starting from the simple pendulum, we like to simplify all oscillations saying that this is a simple harmonic motion, meaning that the displacement is not too far from its mean position. So this is also supposedly, for most light interactions, the displacement is very small from its mean position, so it's actually simple harmonic. But if the light electric field gets larger, why does the light electric field get larger? Because the intensity is getting higher and higher, and the electric field is square root of intensity. So you're going to apply larger and larger electric fields, which means that while the normal day-to-day optics happen at 1 watt per centimeter square or a few watt per centimeter square, and you admire beautiful phenomena like the rainbow and reflections in a mirror and so on. So this is my intensity meter now. What happens as you kick up and go to higher and higher intensities here is very interesting. As the intensity goes up or the electric field goes up, you cannot describe this by a linear motion anymore, simple harmonic. You have to add this to really account for the physics. It develops what is called the nonlinear terms. So this E squares and E cubes start coming in. So the dipole moment is now no more linear in the electric field, but it is actually nonlinear, right? And this is the dipole moment that you now put in here and try and produce the kind of re-radiation that happens. re-radiation or excess absorption, whatever is given by this absorption, radiations, everything is now modified by the nonlinear nature of this expression, and that is because of what is called unharmonicity. Anything deviation from harmonicity is unharmonicity, and squares and cubes and so on. So this is something that puzzles most people when they hear. So you think everything is simple, you know, I mean, absorption is fixed for a system, refractive index is fixed for a system, and if I ask any student here, the answer comes out pat. What is the refractive index of some material? The answer comes out in no time, right? And they think it's a fixed quantity, it doesn't depend on many things. But let me tell you that while the linear refractive index gives you the constants of absorption and the refractive index, the absorption coefficient and the refractive index are constant. The nonlinear, so this is the linear one, n0 and alpha 0, absorption coefficient and refractive index. The nonlinear one actually modifies each of these terms. The refractive index is not the same at high intensities. So the refractive index can become different from the 1.5, 1.6, 1.7 that you have sort of committed to your memory for glass. Glass can have refractive index which is very different from 1.5 at something like 600 nanometers, right? And that is controlled by intensity. It is not by if I increase the intensity more, I can actually reduce it or increase it the way I want. And this parameter N2 is a coefficient. It can be positive or it can be negative. And if N2 is positive, refractive index increases. If N2 is negative, refractive index will go down from what you normally know as the value at a particular wavelength. So if it changes with wavelength, we know it is dispersion. But even at the same wavelength, you can control these parameters dramatically. And imagine this absorption. Absorption is, say, suppose there is a weakly absorbing system which has got a low alpha 0, right? All of you know the Beer-Lambert's absorption law. You have a liquid, you shine light, and then everything decays, you know, the intensity goes down as a function of length, and there is this constant which is called the Beer's absorption coefficient and so on. But now if you send intense light, the alpha 0 may be small, but the alpha 2 into I can be very, very large and controlled by I, which means a normally transparent system can become absorbing. A normally transparent system can become opaque as intensity goes up. Or a normally absorbing system, alpha 0, high alpha 0, but a negative alpha 2 multiplied by I, a normally absorbing system can become transparent. Did you guys know this before? That light intensity can control optical properties dramatically. So that's a very, very exciting thing to learn, that optical properties of light are directly controlled by the intensity of light, and that is the whole business of this nonlinear optics. So, but I am here not to talk about just increasing the intensity a little more. I am talking about intensities which are extreme, right? I want to go not to megawatts and gigawatts of power, where all the things that I just told you right now about absorption changes, refractive index changes happen, but I want to go towards what is called extreme light, right? Now, an extreme light is very powerful. It's a powerful burst of laser light. So you have a laser which emits very, very short pulses, very energetic pulses. So if you take the energy by time, the peak power can be of the order of petawatt. And it's extreme in two ways. Well, it's extreme in time because it's shorter and shorter pulses, so extremely small in duration, and as a consequence, it's extremely large in power, right? So both time and power, or in a related way, both of them are extremes. So, well, it's good to recall that just the last year, 2018, the Nobel Prize was given to 3 people. In this Nobel Prize is a contrast of sorts. So this man, Arthur Ashkin, he got it for using lasers like this, the one I have in my hand, to control, you know, particles, to move, you know, small particles in air, in liquids and so on. And he caused a revolution by what is called optical tweezers, right? And they've been about pushing light with laser light, applying forces on light with laser light, on matter with laser light. So that's what he got. So he used very low power lasers. Come to this half of the slide, and you have Gerard Moreau and Donna Strickland, who won the prize for producing this idea of compressing pulses and increasing their peak power tremendously. So they got it for extreme light, while this person got it for what is called, this species got it for using normal laser light to apply forces on particles. So the forces on particles here are extremely small. The forces on particles that can be applied with this kind of light are extremely high, right? So it's two contrasts, but so it's very topical. This area is got a big boost because of this Nobel Prize. And this is a picture of the 150 terawatt laser that we have here. So you count terawatt is 10 to the 12 watts, and this is 150 terawatt, so you can put the numbers there. And it's a short pulse, 25 femtoseconds. Sorry, this is not 2.5, this should be 3.75. When it was 100 terawatt, this was 25 femtoseconds and 2.5 joules. So that I should have changed, I apologize for that. But this is one of the amplifiers that we have in the laser. And you can see the green light is actually pumping the amplifier crystal here. And the amplifier crystal is actually emitting a orangish, reddish glow. And the red is the laser that is being amplified. So the green is overwhelming this environment here, but the green is actually only pumping the amplifier. So this is 150 terawatt laser, recently upgraded at TIFR. So just to put some feeling for what all these intensities mean, right? So let me compare, we always, as physicists, we like to compare things and say how big or how small. So, and the best electric field for us is given right inside matter. It's a standard thing, right? So hydrogen atom, 1s electron, if you compute the electric field, that turns out to be this value, 1 billion volts per centimeter. Corresponding intensity by this formula is 10 to the 16 watts per centimeter square. So 10 to the 16 watts per centimeter square can apply an electric field of laser light, can apply an electric field which actually matches the Coulombic field inside the atom, right? So if you go larger than this, you become super Coulombic. And currently you can actually access 10 to the 22. So million times larger, 3 orders of magnitude larger in electric field. So I can apply a trillion volt per centimeter field on an atom. What do you think should happen? Should the electron listen to the nucleus and be bound? Or should the electron listen to the light and get excited? So the answer is obvious. What does powerful light do? It does strange things. So let's go back and compare with what you know again. So the photoelectric effect is, you have been taught in your schools and colleges that to cause excitation you need an h nu, a photon energy which is larger than the ionization energy, right? And then the rest of the energy, h nu minus IE, comes out as the kinetic energy with the electron. And you also told that this is very important to match the h nu beyond IE. And you also told that the intensity of the light doesn't matter. It only produces more electrons, right? It doesn't change the interaction itself. So these two are the cornerstones of the classical photoelectric effect. But if you have high intensities, this is what happens. So the photon energy can be much smaller than the gap between the ground state and the ionization limit, but still you can excite it using multiple photons and reach the continuum. And this has been known since the 60s, since the lasers were invented. 2 photon, 3 photon, multi-photon ionization has been known. This is as if the photons build a ladder here for the electron to climb, right? So this is multi-photon excitation, and normal photoelectric effect now has to be modified to what is called multi-photon photoelectric effect. And there is also something else which happens, which is again very not encountered in normal situations, which is that if you keep on increasing the intensity of light, it actually starts changing the energy levels inside the atom. So this is a 1D atom, like imagine 1 by x, q by x potential minus. So you have an electron sitting in this potential. There are energy levels here which are quantized. And now comes a light pulse with an extremely large electric field, and this is what it does. So it adds an extra potential here, plus minus E dot x, right? This E is the electric field, and it actually, if you see this, I had this animation which makes this, the barrier here, the potential barrier is severely distorted, not only distorted, it is changed. It's, sort of the distortion goes up and down on either side depending on the oscillation of the light. That is, every half cycle it is this way, and the other half cycle it is the other way. So this is like the seesaw that we all play with when we were kids. So this is, now what does this imply? It implies that an earlier bound state can now get distorted in such a way that the electron can tunnel out of this distorted barrier. And this is called tunneling ionization, and this happens routinely above 10 to the 16 watts per centimeter square. Right? So if you have very high intensities, the electron, the valence electron certainly, has to leak out of the atom. It cannot stay inside the atom anymore. And for students, this is very nice to imagine, to actually carry home. The photon energy is only 1.5 eV. The ionization energy for a typical atom, for the valence electron, is tens of eV. Right? For hydrogen, we know is 13.6. Right? So you know that in spite of this large value, the photons are still able to excite. And the photon energy does not seem to matter at all in this excitation. It's only the intensity that matters. So this is again a carry home slide. If you have a high intensity laser field, matter will not remain neutral. It is not stable against ionization. So sometimes multiple electrons are plucked out of every atom which is there at the focal point. And it is the I that matters, not the lambda. And all these things happen on very, very short time scales. So this is what is called an impulsively kicked system. It's a delta function which is kicking the physical system, and the structure and dynamics get coupled very severely, and lots of things happen. And this is where physicists start treating, normally the light field is treated as a perturbation on the Coulomb field, but here the formalism treats the Coulomb field as a perturbation on the light field. The Coulomb field is a small fraction of the light potential that you apply, so it can be treated as a perturbation, and light basically controls the entire dynamics. So apart from ionizing, the light also does some interesting stuff. It, depending on the polarization of the electric field, so suppose the light is polarized along this direction, and the electric field of the light oscillates the electron across its mean position, and it gives it a huge amplitude, something like 10 to 100 nanometers, which at very high velocities. And imagine this 100 nanometers is how many times larger than the atomic radius, atomic size. If you say that atomic size is 1 angstrom, so that's 0.1 nanometer, and so this is 10 to 100 nanometers. So it's much, much, much larger than the atomic size itself. So the electron is makes an excursion which is far from its location, earlier location, and then swings on either side, and obviously getting a huge amount of energy. So this is what happens inside an atom in an extreme light. The light pulse comes, ionizes, and kicks it to very, very high energies, and the intensities at which these things happen very, very nicely is about 10 to the 20, anything above 10 to the 16, 10 to the 17 watts per centimeter square. And how much energy is given to the electron? It is huge, and compare this with normal day-to-day optics of 1 watt, which is, like nothing compared to what you have seen. So again, the interesting thing is that the energy that is given to the electron at the end of this oscillation is something like 1,000,000 electron volts. I'll show that to you in a minute. But the 1.5 eV is the photon energy. The ionization energy is about 10 to the 1, 10 to the 2 eV, which is much larger than this itself. And the energy given to the photon, to the electron at the end of this interaction can be 1,000,000 times larger than the photon energy, 1,000,000 times larger. And that is given by this expression. So if you see here, you have 1 micron light, which is, well, ordinary laser sources, and 10 to the 19 watts per centimeter square, you get an oscillation energy which is 10 to the 6 eV. So you can take an electron which is at rest, ionize it, and accelerate it to 1,000,000 electron volts, all on a tabletop, which means you can have tabletop acceleration happening, right? And the electron at 10 to the 6 eV is relativistic because the energy exceeds the rest mass of the electron, and the acceleration that you get for a particle to move from 0 energy to 1 million electron volt, 1 million electron volts in something like 100 femtoseconds to 1 picosecond is of the order of 10 to the 17 times gravity, which is unthinkable, right, in any other interaction. So if light falls on a solid, it does several things. For example, the light pulse came here, it ionized the electrons, oscillated them, and the oscillating electrons then travel to further and further from the lattice sites ionize more and more electrons. At the end of it, you can have a very hot, dense plasma that's excited here. And typically what happens in such situation is that you have a high intensity pulse and you come and interact on a target. And this is a target. I would like you to take a closer look at this. Everything that you can think of is happening here. For example, the ionization is happening, acceleration of particles is happening, and these accelerated electrons, many of them in the form of beams, jets of particles, they go deep into the target and they consist of currents which are megaamperes. Megaampere femtosecond pulses of electrons. What do currents do in the lab if you have a current? The immediate consequence is that you have a magnetic field. The larger the current, the more the magnetic field. And if you have a megaampere pulse, the current should be the magnetic field should be extremely large. And indeed, it produces magnetic fields which are of the order of megagauss. Megagauss is 1,000,000 Gauss, which is more than 1,000,000 times larger than the Earth's magnetic field, right? So I have 10 minutes? Yeah, sure. Okay, so these electrons then cause further excitation here. They ionize the back layer here and then they exit, and the very fast electrons leave this target if it's a thin enough target, and the electrons leaving, they create a positive potential here, and then the ions get ejected. So you have relativistic electrons coming out of this target, you have high energy protons coming from this target, from this layer which gets ionized here, and you have the gamma rays coming from this interaction, because these relativistic electrons collide with ions inside the target and they produce what is called bremsstrahlung, and the bremsstrahlung can go all the way up to tens of MeV depending on how fast these electrons are. So you can cause nuclear reactions inside here, you can have acceleration, you can have extreme conditions here which mimic astrophysics, right? In a small region of density, in a small region of space in this target, you can create conditions which are extremely hot, at the same time retain the density of a solid. Normally we can't do both of these together. If you heat a physical system, it expands. It expands, the density goes down, like water going to vapor, right? How do you keep as water or a solid as a solid, and then give it temperatures which are millions of Kelvin so that the energy density goes up? So the thing is that this is a veritable source of all sorts of physics that you can think of, all sorts of applications from all these particle sources. So this is what is called extreme states, high density plus high temperature, not high density or high temperature. And so this is called high energy density. So one of the applications of high energy density by laser excitation, which is supposed to be useful to mankind, is to take a pellet. It is not done with femtosecond lasers, it's been done so far with nanosecond lasers, but now there's a version of this which also uses a picosecond or a femtosecond laser, which is called fast ignition. But the idea is simple. There is this pellet with the deuterium and tritium, and you are supposed to heat it with this pulses and then compress it, raise the temperature to huge values like this, and at the same time compress the matter to this times 1,000 times liquid density. And if you do it with good efficiency, you can actually have a nuclear power plant based on laser fusion. And this is also called inertial confinement fusion. There's an alternative which is called magnetic confinement fusion, which the biggest machine ever built by man is the ITER experiment in Cadarache, France, and you are welcome to go and read all the details about it on the internet. So high energy density science, apart from being full of applications like laser fusion and particle accelerators and so on, is also a very, very basic interest, because if you look at this, I plot log rho here, the density scales in the universe, and log of temperature, and everything, almost everything that you know is here on this 2D map, right? You can see even Big Bang being mentioned here, gamma ray bursts mentioned here. But the beauty is that this space that we can access in the lab is expanding, right? So we can now access something like, this is 0, so that is log rho of 0. We are able to go to something like log rho of 2 or 3. So that is a good enough density region, and the temperatures we are going up to 10 to the 6, 10 to the 7, 10 to the 8, 10 to the 9 Kelvin. So we are trying to push more and more outward in this region and do experiments in this using various devices, not just lasers. And so hopefully we will cover this, start understanding lots of things about what's happening in solar corona, lightning, even solar core in some near future, what happens inside a white dwarf and so on and so forth. So the beauty is that the inertial confinement fusion is already up here, right? You look at the density scale, the temperature scales on the density scales. So we have already reached densities and things which are very, very hot. So you can read more about all these things in my tutorial review that I mentioned at the beginning. And this is just to say that all dense media produce extremely hot and dense plasmas by various processes that I have just talked about in the last few minutes. Since I'm running short of time, I will just mention a few basics and some research that we have done and conclude. Why is it that high energy density is created by an ultra fast laser, by a femtosecond laser? So this is a very clever technique that it is basically the electrons that absorb the energy from the laser, right? So you kick the electrons, which are light particles, to millions of Kelvin so fast compared to what? Compared to the motion time scales of the ions, right? So this is typically the kind of thing that happens. The laser pulse is in this duration, and the ions typically take something like hundreds of femtosecond or a picosecond to move. So the ions are the ones that actually form the lattice that give the density to a piece of matter. While the electrons take the energy and get hot, they become a very hot subsystem excited to very, very large temperatures. The ions are stranded there because they cannot move. Eventually they will, but within the femtosecond of excitation they cannot move, right? Within laser pulse excitation. So for a short time you have high energy density. For a picosecond or a few picoseconds you have high energy density that you can observe in the lab, which mimics astrophysical objects. So let me skip this and say that I have done all this. This is what is called laboratory astrophysics, and I'll just tell you some things that we have done in the lab. So in the lab we create these plasmas on a target here, and then the light comes and reflects from what is called a critical layer, where the electron density is so large that the light cannot penetrate further. So this is a wall inside the plasma from where the light reflects. But we have used this technique, but this is how interaction happens, that you shine a laser beam, so the electrons, the light cannot penetrate further, but they can create electrons at this critical layer. These electrons go inside the target and they create very, very strong excitation, very hot conditions in that dense medium. So most of our work at TIFR over the last decade has been looking at how fast do these electrons move, how do they exchange energy with this, the rest of the system, the bath there, right? And what happens to these electrons eventually? Do they propagate like a jet? Do they break up? Do they diverge? Do they go somewhere else rather than going straight? So various physics questions, and our typical experiments are done by what is called a pump probe method. We have a pump pulse that creates this plasma here, and a delayed probe pulse comes that then probes it at different times. So every time, every laser pulse is split into two parts, one pump and one probe, and the probe can be delayed for each pulse at distinct time intervals. So this is how, just to enthuse you that experiments are very exciting. So let me show you how this is done. And this is done by students like you, I mean when you graduate and enter TIFR. So it's not complicated at all. We have a plasma here, we have a probe pulse. The probe pulse reflects from here and then is coupled to various detectors for getting various pieces of information. Some of our major results have been about this magnetic field that I said, which is created. So in our lab, we measured out magnetic fields which are a whopping nearly 70 megagauss, right? 70 megagauss fields. We were the first ones, TIFR was the first one to show that this magnetic field lasts all of 5 or 6 picoseconds. It is not long-lived at all. People thought that nobody knew how long this lived. We were the first to provide this information, and we also mapped out its evolution in space and time in the same experiment. So these are, here time is ticking, and here I captured 2D evolution of, so across the plasma interface, what these magnetic fields are. And you can see that these magnetic fields look rather sort of very, very weird. They have lots of spikes, there's a spiky structure here, and they look totally inhomogeneous and so on and so forth. But we have captured this entire evolution. And in spite of the fact that they look totally unrelated to each other, if you see the power law that they follow, this is the magnetic field energy density versus the inverse length scale. So it's called the power spectrum. And the power spectra fall beautifully parallel to each other. And when you power phase spectrum has this kind of a slope, or it displays this kind of a behavior, it is supposed to be a turbulent kind of magnetic field. And the details, of course, you can ask me later. And this is what is called magnetic turbulence in a tabletop laser plasma. And this is what happens in the heavens. It happens in the solar wind, it happens in the solar corona, it happens in similar, even in Earth's magnetosheath. So now you had asked me, so what does this mean? It means that I can model the solar corona by doing an experiment in the lab, seeing the same kind of behavior, mimicking the behavior, and maybe then if you have a model for how the solar corona evolves, I can test it out with my data. So I can push astrophysics, and I just put this in just to show that this is not a commentary that we wrote. It was written by Nature Physics, and it says, wouldn't it be handy to have your own sun, miniaturized solar system in the lab, offering the chance to experiment with astronomical events with relative ease, right? So this is a very lofty statement saying that you can create your own miniaturized sun in the lab and keep observing it, before lunch break, after lunch break, on Saturdays, like whenever you want in the night, come and switch on the laser and there you have something that mimics the sun. So, and this is a commentary that they wrote about turbulent tabletops, about the paper that I just mentioned. So we have done several other things on plasma motion. We showed that the plasma sort of breathes in and out, or it shakes very violently at terahertz frequencies. This is actually an acoustic oscillation unobserved by anybody else in the community, but we were the first to capture it. So this is what I called trembling at terahertz. So the plasma literally trembles at terahertz frequencies. So let me leave that and go straight to one more experiment where we actually captured the electrons moving inside the solid at relativistic speeds using what is called Cherenkov emission. But these are highly technical things, so I didn't really want to tell you that. But I want to leave with this thought about where we are going. So this march up the scales has been, as I told you, very, very strong, inexorable march towards higher intensities. People are now thinking of producing lasers which can produce intensities of the 10 to the 23 to 10 to the 25 watts per centimeter square, which means that we had this atomic era where we could think of atoms responding to light, then electrons still staying inside the atom. Then we have the plasma era, we have the positron electron era, as people call it, around 10 to the 20 to 22 watts per centimeter square. And the positron electrons are produced by gamma rays breaking because of pair production. And then we go higher and we approach things like particle physics. So the bottom line is that high energy density science is extremely exciting. It deals with extreme states which are prevalent in most of the visible universe. Obviously must be studied because that's what science is all about. And on a tabletop, it opens up dramatic applications in particle sources, which can be used for as accelerators for other applications. For medical therapies, you can kill cancer cells with some of these beams that are produced by this, and what have you. I mean, you can think of more applications. So it's a great field to join. So some of you, I hope, the Olympiad winners, medalists, right, will be encouraged to enter basic research in this field because it combines lots of areas in one tabletop. And so this is what I also call the descent of the heavens, right? And I've called it stars on a tabletop when I gave this talk at the Prithvi Theatre in Chai and Wai. I actually called it Tare Zameen Par. And all of you know, you know about the brief history of time, right? All of you have known this book by Stephen Hawking. So I call this a history of brief time, just punning on that. And so the people who have contributed to this work are many, students, past, present, postdocs, colleagues. My colleague M. Krishnamurthy, who is another faculty member at TIFR. So both of us lead this activity here. We are also trying to expand into Hyderabad in a new campus where we'll have our own petawatt laser. So there's some more pictures. That's me in the lab with the laser. And thank you very much for all your attention. I did exceed my time, so I hope. Okay.
If you have questions, please.
Questions, challenges? More like, I don't believe what you said.
So,
Yeah.
so I have a question regarding the refractive index that you mentioned, that it depends upon intensity.
Yeah.
So if that in the slide it was saying that, let's say the refractive index is some A0 plus A1 times intensity. So is it possible that A1 times intensity is somehow makes the whole refractive index negative?
Well, that's a good question. Should be possible, right? What I mean is, first thing you should ask me is that I reduce it to 0. What does it mean?
That was my conclusion.
Right? So that means that things like the velocities of the speeds of light will change dramatically depending on what the refractive index is. Right? So it is possible, what you asked is eminently possible, but you need to find a system for that. But there are, this is purely classical way of looking at things. There are quantum ways of looking at it where you can have what is called the quantum interference. It's beyond this right now, where you can call what is called electromagnetically induced changes of refractive index. So refractive index changes, either understood this way or in the quantum mechanical way, are perfectly possible. And nobody is surprised when you say, like for a typical school student who has been taught that group velocity cannot be larger than c. Everybody agrees? The Olympiad guys, what do you say? Group velocity cannot be larger than c. Agree, disagree? Can we vote? It can be larger than c. Group velocity can be negative, right? All these are effects of, but they are not in the sense that they don't violate causality, because they don't, the true signal, the information is conveyed in a signal which has only a discontinuity, which is like a step. And the step can never go faster than c in any medium, no matter what the conditions are. So for continuous pulses like Gaussians, wave packets, group velocities can be anything. This has been investigated heavily in the last couple of decades. So the short answer to your question is, it is possible. That you need to find the appropriate N2. And by the way, I sort of glossed over lots of things. N2 is also a function of lambda. So in the visible region, N2 can be one thing, and N2 can be very different in the infrared region, right? So there are various contributions to making this N2. So you have to be careful about which region you are at, and the windows in which all these effects happen can be very small. I mean, they can be in a narrow window of wavelengths over which these manifestations of extremely large refractive index can happen. So it's not across the spectrum, nor is it across all materials. So, but that's a good question.
Thank you.
Yeah. And if you, I should go back to my, well, this is our website. In case you are, hesitant to ask questions now, you can always visit and post things on this website here. And my email, I think you have, it's grk@tifr.res.in, which was there on the first slide, but I'm sure you can find it from the brochure that you have. Right? So please do shoot questions and ask us, visit our lab when you can. We'll be happy to show you what we are doing. And do take up this area when you grow up. Yeah.
I have a question.
Yeah, please.
Are there any other questions? Okay, then I have a question. So,
Yeah.
what is the technological barrier in compressing it more? You already have femtosecond at TIFR, and then you're talking of also zeta watt lasers. So how does one, compress this within this short time, and what's the technological barrier?
Okay, so people have moved on from femtoseconds. In the last 20 years, people talk about attoseconds. And attoseconds is 3 orders of magnitude down, 10 to the minus 18, right? And all of you watch Big Bang Theory by any chance? You did, right? In one of them, there is a question. There's a quiz, and Sheldon, of course, answers the question, saying that what is the shortest pulse known to man? And he mentioned some several hundred attoseconds, right? And right, though Sheldon is always right. So, and the interesting thing was, so it is as popular as that the attoseconds have been breached, the barrier is now there, but the attoseconds are produced from femtoseconds. Now people are thinking of ways of creating high amplitude attosecond pulses by using high amplitude femtosecond pulses. But that is still at a very critical stage. You are right. I mean, if you want to shrink to, people are talking about exawatts of power, which is 10 to the 15, now 10 to the 18. How do you go to 10 to the 18? And it's obvious to most people that you have to go to that regime. And that regime is not in the visible region at all. Because these are, one of the extreme nonlinear events is that you take a visible photon and you can get a harmonic which is 1,000 times. So a visible photon can be converted to an X-ray photon. And the X-ray photon is what is really that attosecond pulse. So the X-ray photon exists in KeVs or hundreds of eV. So these are not going to be in the visible region. They will be necessarily in the X-ray region. But having said that also, the dramatic increase in light intensities has been in the visible domain so far. But now the latest is X-ray free electron lasers, which can now produce X-ray pulses of femtosecond duration, KeVs, beating the synchrotrons at their game and producing intensities which are 10 to the 15, 10 to the 18, like that, right? So I know that I have grossly run out of my time, but if I have just 1 minute, I'll show that video.
Sure.
Right. Okay. Can I get this? Yeah. So since you guys could not come to the lab, I have mic laga denge yahan par. So I brought my lab with me here. So let me show you. It'll just take a couple of minutes. I just want you to watch this. So that's our lab in TIFR. And you have a light pulse which is falling here. That's a femtosecond pulse. And I want you to see what happens when it is focused. Okay, so there is something happening. It's being focused on a target here. Well, you see more in the next slide. You see there's a metallic target here. And the light, it's actually infrared light. You can't see it in the vacuum chamber. It's being focused at this target here. And what do you see? You see a blob of very high excitation. That's the plasma that's been produced by the laser. And it's also making sound. This was not done in vacuum. This was done in air. Sorry about that. And so it is producing sound. So maybe at the end of this session, you tell me what is the sound that you're hearing. And what does the sound remind you of? What does it remind you of? See that? It's every time the laser pulse falls, there's a blob of plasma that comes out, and you're hearing the sound. This is all done in an open chamber. Experiments are done in a vacuum condition, but this is done in air, and you hear a sound. So at the end of it, at lunchtime, you can tell me what the sound is all about, and I shouldn't take more time. So thank you very much for your attention once again. Yeah.
Thank you, Professor Ravindra Kumar.
So I look